Karnaugh maps can be used to give a minimal representation of a boolean expression. So if we have some boolean expression e, that represents some boolean function f. So for example, this may be x and y, or x and z, or y and z. Then we denote the number of terms that are summed. So in this case it's 3. And a number of literals, EL, as 6. So we have 6 literals, and that includes repetitions. So we call E a minimal representation of some boolean expression if for any other boolean expression f, where both of these represent the same function, we have the number of terms in E being less than or equal to the number of terms in f, and if the number of terms in the expression E is equal to the number of terms in f, then the number of literals in E must be less than or equal to the number of literals in f. So this must be true for any expression f that represents the same function as E. And these minimal representations don't need to be unique. So for example, the following expressions are equivalent. And I'll let you verify this using algebraic manipulation. So these are equivalent minimal expressions. Now one more thing we need to consider with Karnaugh maps is adjacent terms. So two product terms, such as x bar, y, z bar, and x, y, z bar, are called adjacent if they differ by exactly one literal. So in this case, these product terms are adjacent because, as we can see, only one literal differs between them. And the differing literals are complements of each other. So another example, if we look at 4 variable product terms, we have w, x, y, and the complement of z being adjacent to w and the complement of x, y, and the complement of z. So as we can see, all the literals are the same, except x and its complement between the two product terms. And an example of terms that are not adjacent are the complement of x, y, and the complement of z, and x and the complement of y and the complement of z. So as we can see, these terms differ by 2 literals. So they're not adjacent. And here is another example of terms that are not adjacent. So we can see that w and its complement differ between the 2 terms, and z and its complement also differ. So now looking at these Karnaugh maps, and specifically we're looking at 4 variable Karnaugh maps. And when we label this Karnaugh map, we have the terms in the columns being adjacent to each other. So as we can see, they differ by exactly one literal. So we have x and its complement being different between these 2 terms, and w complement being different between these 2 terms, and x and its complement being different between these 2 terms. So each term is adjacent to the next one, and the final term is adjacent to the first term, as we can see, because these differ by w and its complement. And in the rows of the Karnaugh map, we can see that y and its complement differs between these 2 adjacent terms, and z and its complement differ between the next adjacent terms, and y and its complement differs between the next adjacent terms. And the final term is adjacent to the first term, because these differ by z and its complement. So the labeling in this case here is not valid, because as we can see, these two terms are not adjacent to each other, because they differ by more than one literal. So here we can read A as w bar x bar y bar z, and the terms adjacent to A are these ones over here. So A1 is w bar x bar y z. So as you can see, these differ by exactly one literal. And A2 is wx bar y bar z. So as we can see, only w bar and w differ between A and A2. And I'll let you verify that A3 and A4 are adjacent to A. And the terms adjacent to B are as follows. So as we can see, the representation of B is w x y z bar. And if we look at B4, that's w x y z. So these differ by exactly one literal, and therefore these two terms are adjacent. And you can also verify that B1, B2 and B3 are also adjacent to B. So we can see in this invalid Karnaugh map that C1 is not adjacent to C, because C is x bar y bar w z bar, and C1 is x y w z bar. So these two terms differ by more than one literal, so they're not adjacent. So we can see that Karnaugh maps can be used as a shortcut to represent different boolean expressions, and we'll cover more examples on Karnaugh maps.